Now, before we get started, I'll introduce our speaker. Dr. Adam Naples is an assistant professor in the Child Study Center at the Yale School of Medicine. As a researcher at Yale, he has co-authored papers on autism, reading disability, and genetics, and developed novel experimental methods for studying brain activity during live and simulated social interactions. His primary research interests are understanding the neural and cognitive mechanisms that lead to variability in developmental disorders. Dr. Naples was a recipient of a 2022 scientific research grant from the Autism Research Institute. These webinars are made possible thanks to generous donor support. If you'd like to contribute, please visit our website at autism.org. And now I will turn this over to our presenter.
All right, thank you, Denise. So it's good to be here, and thanks for having me. And today I'm going to present on an ongoing line of new research that's supported by the Autism Research Institute. Our focus is on studying the measures and mechanisms underlying auditory sensitivities, primarily in autism. But as many of you know, many people experience maybe complicated relationships with the sounds around them and in their environment. Denise is going to monitor the Q&A. If anything is unclear, please, I guess, put that in the Q&A, and I'll have some time afterwards to ask for questions and if anything needs clarification. So, all right. A little bit about myself. My background is I'm a cognitive scientist. I'm not a clinician. I'm not a therapist or a psychiatrist, but I work closely with many. And I've been interested in auditory sensitivities for a long time. Many years ago, I started studying music therapy in music school, which really kind of opened my ears, I guess, to the many ways in which people experience sounds and the diversity around that. And I've been working to get my way back to this research area. I think it's important that I approach a lot of this work through the lens of the cognitive science tools, right? We all have different toolboxes as we do research, how we see things, and there's other tools and lenses that people can carry out the research in. So briefly, I'm just going to talk about a brief overview of auditory sensitivities in autism, and then drill down to three specific research areas. One is some research we've done trying understanding how our current measurement tools can help us to identify and maybe target biomarkers for sensory function. Two, developing some approaches to measure the stability or the fluctuations and changes in sensory sensitivities within a person over time. And then some preliminary data linking these sensory sensitivity measures to more lab-based biomarkers, so neuroscience that we do in the lab. So brief history of auditory sensitivity in autism. In the earliest reports of like Connor's 1943 paper in the 40s and 50s, there were explicit quotes I can repeat here that not less than 7 of the children were considered as deaf as hard of hearing, right? So there's an acknowledgement that autistic children and people had a different responsivity to sounds from the earliest reports, right? And in the 40s and 50s, auditory hyposensitivity or reduced responsivity to sound was noted. These observations generally looked like caregivers thought these children were deaf, but when further research revealed that these kids were sometimes sensitive to specific sounds, and that the sensitivity referred to lots and lots of different things. In the 90s and to the present, we've actually seen a little bit of a shift, which is we're seeing more self-report. People are reporting on their experience, autistic people. And they're reporting often being more sensitive to different kinds of sounds. And again, the sensitivity manifests in multiple ways. And throughout all this research, a few things pop up. One is that hearing, when I say hearing, I'll use this a few times in the talk. I'm talking about air conduction hearing in your ears, right? Are your ears okay? Audiometric thresholds. Hearing is, for the most part, normal and not associated with the kinds of concerns and sensitivities people report. And the kinds of sensitivities people report are highly heterogeneous. And so there's kind of two things to highlight here. One, the taxonomy for how we describe the auditory sensitivities is emerging. And two, one thing that I want to highlight is how do we reconcile the differences in the kinds of reports people have had with hypersensitivity and hyposensitivity, because this is all very solid research for the most part, but we're seeing inconsistent findings. So broadly, when we talk about auditory sensitivities in autism, in some reports, they're present in up to 70% autistic people, and they include increased and decreased sensitivity to sounds, right? So that might be sounds are too loud or sounds are hard to hear. These sensitivities worsen with stress, fatigue, and they're also associated with other kinds of challenges, such as maintaining attention, anxiety. Again, these sensitivities are not associated with different hearing thresholds for the most part. And there's also few really consistent findings within the field. And this has led to limitations in understanding what the mechanisms underlying these sensitivities could be. And without understanding mechanisms, like why we're interested in mechanisms, it makes it really difficult to do a few things. Like one would be to develop effective treatments for people. Two, to know who is going to be more or less sensitive, why or when. To know when a treatment may or may not be working, or who might benefit from a specific treatment. Also, just to understand why these sensitivities emerge, and also to develop strategies to manage them. So I want to highlight that these sound sensitivities, and I think this came up in the Q&A, and I apologize because I can't. It's difficult for me to monitor the Q&A completely while I'm giving these, and so Denise, if there's something that I really should attend to, please let me know. But the sound sensitivities encompass many things, right? And so a common term used to describe this is decreased sound tolerance, which can include things like aversion to sounds, being more distracted by sounds, difficulty paying attention to speech and noise, or other things that you want to pay attention to in noise, but speech being a particularly important one, and fear of sounds. And also the way people approach this is with really highly variable accommodations. And then here I just also want to highlight that these sound sensitivities are a broad enough concern that many of our computers and cell phones are incorporating technologies that help people shape their auditory experience in different ways. And so just for example, on my computer, I can set background sounds so things are less distracting, like dark noise or ocean sounds. And my headphones can actually amplify things that are in front of me and suppress the sounds from things that are behind me or beside me, which can help to amplify a speaker if I'm talking to someone. So now, just to give you a little brief overview of the impact that these kinds of sound sensitivities have, and this is from this paper below. People adopt many strategies to deal with sound sensitivities. So some of these are sort of covering ears, using earmuffs to block out sound. It's immediate, noise canceling headphones. These are things that people can carry around, earplugs or earphones, or getting themselves away from the sound source. There's also family and caregiver strategies where you're trying to warn the child about upcoming sounds. This is a paper about children, avoiding noisy settings, creating quieter environments if possible. But these aren't, there's the earplugs in the top right corner. But these accommodations aren't without cost, right? And so some of the costs include things like reduced participation in family activities, school activities, community activities. In some cases, there's safety concerns. If you're going to leave school because of sounds, that's well, I guess maybe to put it another way, you shouldn't leave school because of sounds and not tell anyone. But it is possible for this sort of events to occur. And also there's just an emotional burden on families because, as I mentioned, the strategies for coping with these sensitivities aren't always 100% successful. And so, managing this is takes a cost on people and their families, and in both the emotional burden, but also in the reduced participation, family, school, community. So now I'm going to give you a little more clarity on the kinds of thing I mean by auditory sensitivities, and I'm going to focus mostly on the bottom two types here. And the review article shown to the right is comprehensive and excellent, and it's so I recommend it for more detail. Briefly, tinnitus, I think many of us have heard of this before. This is called a phantom perception. It's when you're hearing a sound and there's no acoustic input, commonly a whooshing sound or a ringing sound, and it can occur after hearing damage. Phonophobia is a specific phobia of particular sounds, resulting in fear, anxiety, and avoidance of sound sources. And it can develop secondarily to these following 2 points: hyperacusis and misophonia. And it can occur when individuals become fearful of encountering aversive sounds. So now let's talk about hyperacusis, which is, I think, one of the most common terms people hear. Which refers to an intolerance of otherwise ordinary sounds in the presence of normal, again, air conduction hearing. But there's not a universal agreement on definition. And so on the right, I just am showing you a brief screenshot of the hyperacusis questionnaire. And I want to point out that the kinds of questions range a really broad area of experiences and include many of the concerns that people with autism have. But things like, do you use earplugs or earmuffs to reduce your noise perception? Do you have trouble reading in a noisy or loud environment? Do you turn down an invitation or not go out because of the noise you would have to face? So here we've got, we're looking at attention, we're looking at ways to directly reduce input, or behavioral strategies or coping strategies. And anticipation. Do you have difficulty listening to conversations in noisy places? And so, really we have a mix here of hyper and hyposensitivity. And I want to highlight that in many of these cases, these concerns are more complicated than just a sound is too loud or is not loud enough, right? Like they reflect, the way people filter sounds, the way people sort of conduct their lives around their experience of sounds in a way that might be disruptive and they'd like to have a little more control over. So there's hyperacusis. Misophonia is another more relatively common occurrence, which refers to a disorder of reduced sound tolerance. And a specific aspect of misophonia is that sounds elicit very, very strong emotional reactions, most commonly anger and disgust. And these emotional reactions, are typically sounds made by other people. Things like breathing, chewing, eating, but not always. Also, people with misophonia often describe a hypervigilance to these sounds differently than phonophobia. So not necessarily, a fear, can be a lot along with phonophobia, a fear of the sounds, but even after a sound is abated, people describe a feeling of not being able to let their guard down, right? To let their attention kind of get back to whatever they were doing, lest the sound return. This, dysregulated hypervigilance. And this is captured in that, this distress that persists after the sound is abated. And the way I think about misophonia, and one of the ways it can be particularly burdensome, is just like, imagine you're in school trying to pay attention in class, somebody starts chewing, right? And this elicits distress, a strong emotional reaction. And even after they stop, some people might still be so vigilant and so worried the sound is going to start up again, that their attention's still focused on it. The sound is gone, but they're still carrying this toll attentionally that is interfering with being at school, with whatever you're working on learning at school. Right. So now, remember, I mentioned one of our primary goals is to understand mechanisms, and we hope this will help us develop better treatments and interventions. And now I want to talk about getting some perspective on the way we measure this. So again, many of us have a pretty rough or a very clear idea of what these sensory sensitivities mean. But Well, what we did here is we really wanted to look at the way we measured the way we currently measure these sensory sensitivities, um, trying to just understand sort of the information they capture and use that to help us sort of target biomarkers or ways we can measure these sensitivities more objectively. Currently, how do we measure sensitivities? For the most part, we ask about them. And these are sample items from a range of different measures that we use. The measures are in the bottom right. The items are listed there. And I want to emphasize that, this is a range of different assessment tools. And this is just a drop in the bucket. There's many, many, many assessment measures out there for measuring sensory sensitivities that are specific to sounds or more broadly general to all sensory modalities. They really demonstrate a breadth of concerns. And I would show this to illustrate, the diversity of what we're measuring and why understanding these mechanisms might be so complex. So, but if we look at these measures, one thing I thought about when I first started doing this research is, are they really measuring the same thing? And so these items and the measures themselves tend to probe different aspects of sensory sensitivities. So at this top, do you find certain noises that sound annoying? Broadly, we can consider this hyper or hyposensitivity. Whereas, not making sense of sounds at all, it really captures sort of this distraction attention aspect that people describe, that some people describe when struggling with sounds. This third item, I can hear electricity humming in the walls. I think it's interesting for a few reasons. One, it's not valenced, right? Unlike this first item on sound being annoying, it's not asking if someone dislikes or dislikes the sound. But two, and this is important, is this highly reporter dependent. Because sometimes electricity might be humming in the walls and you don't hear it. Now, it's not clear, though, if you would respond that you can't hear the electricity humming in the walls, because maybe you think you only report when you do hear the electricity humming in the walls. And so it raises questions about whether we're measuring, to what extent these measures are able to capture the full breadth of sensitivity. And then finally, this last item, is very dependent on the observer, on the self versus other report, in that it's very reporter dependent. It relies on someone else observing a behavior and making a judgment on, or at least having some baseline definition of what unusual means. So it adds an additional layer of interpretation. So, but we can also look at these. So we can look at the measures in one way. There's these items probing many different domains, but we can also think about how we could use these to maybe capture some underlying biological mechanisms, right? How can we use these questionnaire items as clues to guide us there? So we have a few questions that we use these measures to approach. And I'll show you how in a moment. But one, are some people hypersensitive and others hyposensitive? So going back to the start, I mentioned that there's some reports that describe people with autism as hyposensitive to sounds, others as hypersensitive. Or are some people both hyper and hyposensitive, maybe at different times or in different contexts? Are sensory sensitivities strictly limited to specific modalities, right? Like sounds, sense, or are they broad reaching across multiple senses, which might help narrow down neural mechanisms to specific sensory regions or brain mechanisms that modulate sensitivity in other regions. Many things change in development, and so understanding how these sensitivities may evolve or change over time can, again, help us learn where to look for mechanisms. And finally, we, in the search for biomarkers and sort of mechanisms, I guess we're always in the kind of research I do, always trying to find like those perfect questions that really capture the underlying biology. And so we want to know, are some questions really much closer to the underlying biology? So let me tell you how we did this, though. And this is a manuscript that's currently in preparation. Is we used data, big data, from the NIMH data archive, where we downloaded data of 7,900 participants across 122 studies. with 12 sensory measures over here on the right, to ask these questions. Are we finding that people are hypo or hypersensitive or both? Are these sensory sensitivities modality specific, and are they showing developmental change? There's, of course, more than 122 studies in ENDAR, but these 122 in 12 measures show the greatest amount of overlap, which allowed us to really leverage data across multiple studies. And so here's the first thing I'm going to show you. And this is just a simple plot of auditory hyposensitivity on the y-axis and hypersensitivity on the x-axis. And what this is showing us is that for the most part, the same people who are hypersensitive are also hyposensitive. Also, you might notice that this is not showing 8,000 points because not every single person did every single measure. So this is, the sparsity of it. But we are showing that the same people who are experiencing sort of sensory extremes in both directions, which makes me think it's not that some people are chronically and tonically hyposensitive to sounds or hypersensitive, but rather they might be experiencing some spending more time in the extreme states of sensitivity. And secondly, we wanted to know, how specific are these sensitivities to modality? On the y-axis, again, now we have visual hypersensitivity. On the x-axis, auditory hypersensitivity. And we find that across modalities, the correlations are as high as they are within modalities. If you have high levels of visual sensitivity, you have high levels of auditory sensitivity. And, this is important because I think it suggests that some of these sensory sensitivities aren't modality specific. When many people have auditory concerns, a reasonable first line of the person you reach out to is an audiologist, and I'm not suggesting people don't do that. However, the data we're showing here suggests that it might not be something that's so specific to the to hearing, as we've seen before, and maybe there's more general mechanisms at work. And do relationships change with age? Again, we see the similar pattern of results, and this is from the sensory profile for children. We see strong correlations between sensory avoiding and sensory seeking. And so, right, those are 3 scatter plots. But what if I were to show you this sort of complicated plot? So I'll take a minute. This is a matrix of all the correlations among all the measures, among all the people. The color tells you whether it's positive or negative. Each dot tells you the relationship between one measure and another. And so I'm not sure if you guys can see my mouse here. Hope so. But you'll see that for the most part, every single dot here is blue, indicating positive relationships. Like if we're more showing increases in one direction, showing increases in another direction. People are hyper and hyposensitive. This is across the lifespan, and this is across sensory domains. These little islands of points reflect areas where people overlapped in sensory measures. And for example, like this here might be the Glasgow Sensory Questionnaire and the sensory gating inventory. Not every single person in every study completed every measure. And there are a few red ones, which of course I was like, well, okay, what do those mean? And for the most part, these places where we're seeing negative correlations are where the measure itself forces the dichotomy. So someone, the specific measurement tool requires that someone be either high or low, but they, they can't show elevated scores in hyper or hyposensitivity. If this were sensory specific, right, we would see little blocks of islands within squares that indicated things like vision or audition, right? We wouldn't see this pattern of, this sort of cerulean quilt here. And if some people were high and some people were low, we would see many more low correlations and more red correlations, but we're not seeing that here. So the evidence suggests that the more you have hypersensitivities, the more you have hyposensitivities. So again, I'm thinking that, maybe it's rather than people having these tonic levels of increased or decreased sensitivity, they're experiencing more extreme states, right? Like sometimes things are more sensitive or sometimes they're less sensitive. All right, so If they're hyper and hyposensitive, this means that the sensory apparatus can change in sensitivity. And so it suggests to me that something about the systems that regulate the sensitivity are important, right? Like, why are things higher or lower sometimes? Because we're seeing these correlations among modalities, this is making me think, like, what kinds of systems in the brain are really broadly distributed rather than specific to, say, visual cortex or auditory cortex. We didn't see any obvious developmental trends or changes, but again, this is a first pass with a lot of data, so we stuck to relatively simple models. And so again, it makes me think about this idea of more extreme states rather than just high or low all the time. So we have two directions that we're going to go on from here, is that, we think people are experiencing more extreme states. So we can actually try to directly test that. Are people higher sometimes and lower sometimes in their sensitivities? And two, maybe instead of focusing solely on auditory sensitivity, I realize I say that it's a little confusing, solely on auditory systems in the brain, we might want to integrate some understanding of the systems that really modulate the sensitivity of our auditory cortex. So how do we do that? And so how do we measure these extreme states? And I'm going to introduce you to this new word called chronometry, which reflects the way in which these symptoms change over time, right? Prior research, again, I mentioned it was inconsistent, but if people are having more extreme states of high or low sensitivity, then you're really caught by the timing, right? People may have participated in studies when they're hypersensitive or hyposensitive, or on average, maybe most people have relatively normative or unremarkable sensory experience. We also typically use these self-reports, as I mentioned before, and they exhibit a few biases that are important to mention. One is we tend to remember when things were the worst, right? It's not to say those aren't meaningful and impactful times, but they may not capture the day-to-day sensory function of a person. And we also tend to report on things that were the most recent. But I also want to highlight another reason why measuring this may have been difficult in the past. As I mentioned, reduced or decreased sound tolerance, auditory sensitivities, they impact participation in things. They impact people going to work, they impact people going to school. And it's likely that if things are bad on a day, or particularly bad for someone on a given day, though that might not be the day that they want to come down to New Haven, find a place to park and participate in a study in a lab, right? They might want to stay home that day. And my guess is that some of these extreme states of sensitivity actually impede participation, creating a challenge to the kinds of research we've been doing in the lab thus far, not just us here, but broadly in general. So we thought, like, well, sensitivity is changing in these extreme states. Well, can we catch it in the act, or can we at least measure these to some extent? And so that takes us to how are some new methods on measuring stability in auditory sensitivities. And so briefly, now I'm going to give you guys the 6-minute overview of auditory perception broadly outside of autism for some relevant facts. This is their own field. I'm not an audiologist, but there's aspects of auditory perception that are pretty universal to humans and that help frame the kind of concerns that people with autism are having. So, and many of these might not be immediately apparent to us, even though most of us have ears and hearing. So, auditory perception, the ear has a huge dynamic range. We can detect sounds from the barest whisper to these incredibly loud sounds like at a rock concert. This is a billion-fold increase in differences and change. This is a tremendous dynamic range. And this range adapts to our environment to change our auditory sensitivity from moment to moment, whether we're at a rock concert and we want to hear different songs, or it's late at night, everything's quiet in our house, and then we hear our baby or our dog in another room waking up and very, very fine sounds. Two, this change of sensitivity is really controlled in your brain, right? Like if we see a really bright light, we can look away, we can close our eyes, our pupil constricts. Our ears got fewer options and you can't really close your ears. So a lot of this sensitivity is actually managed centrally in the central nervous system and brain. If you're in a deep sleep, it takes a really loud noise for most people to wake them up. If people are very anxious, right, or very highly aroused, their sensitivity can increase. And the sensitivity also varies and is modulated by our task demands, whatever we're doing. So maybe that's listening to someone speaking, or again, trying to hear if our baby or our dog is waking up in another room. And this sensitivity is managed by some distinct brain mechanisms. And so, which we'll go into more detail on later. But when neuroscientists, and I think many of us think about neuroscience of auditory processing, we think about the auditory cortex right up here, and for good reason. This is where a lot of high-level sounds are processed: speech, music, sounds. Sorry. All right, there we go. But a lot of activity in the auditory cortex has really back and forth reciprocal connections with attentional regions, right? Sounds we hear, they change our attention. Many of us experience this, and our attention correspondingly helps us filter our experience of sounds, right? So these more general purpose attentional mechanisms really alter like the activity happening in our auditory cortex. And these attentional regions also influence really low-level brainstem regions that control things like sleep, wake, arousal, emotions, and importantly, right back up, mediate our auditory sensitivity. The auditory cortex has got more recurrent subcortical connections than other sensory cortices, and they are responsible for mediating these overall state changes in our perception of sounds. So it's important to highlight here the takeaway: our experience of sound is not some static, stable thing. It's really intertwined with the brain systems that modulate our attention and direct our attention. And something is beeping, so I'm hoping that's Denise. You'll let me know if that's on our end.
Yeah, we can't hear it. I can't hear it.
Okay, great. I thought it was you texting me on my phone, so I just wanted to make sure. Okay, so just to take away from that, auditory sensitivity changes from moment to moment, mediated by distinct neural systems. But as many of you know, right, there's clearly significant individual differences in all of these mechanisms. And so what we're trying to do is understand, what's going on. What are those individual differences? What are the mechanisms of them? And so this takes us to this body of this study, which we call the GAIN study, for measuring symptom chronometry. Again, chronometry refers to the dynamic variation of symptoms. And as I mentioned, the first thing we want to see is, are these symptoms changing? And are they changing more or differently in autism? So we think these symptoms, well, we know that sensitivity changes from moment to moment. We don't know if symptoms do. But on average, maybe auditory sensitivity is no different in autism. It's the more frequent extreme states. And again, maybe prior research has suffered from some of these sampling approaches. So this is the GAIN study, which we have a lot of fun acronyms for it. But this is funded by the Autism Research Institute, totally new line of research for us, and involved getting a lot of ideas working that we weren't sure we could do. And I want to highlight again, we are still actively recruiting participants. And so if people are interested in participating, please let me know, and I have more information at the end. So what are we doing? We have online psychophysics and some in-person EEG, which is preliminary, I'll mention later. But online, what we do is we ask people about their concerns every day for 2 weeks. And we do some psychophysical auditory experiments over the phone. I'm going to talk about auditory sensitivity, but if we have time, we can talk about attention afterwards. Takes about 5 to 10 minutes a day. And the way this operates is, 5-10 minutes a day. Our first symptom measures. These are symptoms. We're asking people about their experience every single day, right? These are state, not trait questions. We really want to measure observably, or at least reportedly and explicitly, what happened that day. And so rather than asking someone, did sounds bother you today on a scale of 1 to 5, we just say, did today some sounds were annoying, right? Not at all, 1 to 3 times, more than 3 times. Today I left work. These are all items adapted from established measures. We probe domains about anger, avoidance, sounds being distracting, sounds you having to leave the environment, sounds that were difficult to ignore, sleep, stress, and strategies people may have applied. So we also do directly measure auditory perception. So this was brand new. Again, thank you very much, ARI, for helping us get started with this. We weren't sure if it would work. We tried 30, 40 different things that needed to be iterated a few times until we got to this. What we're doing is we're measuring someone's tone and noise sensitivity. This is a task that's adapted from many animal models of auditory sensitivity. And the way it works is like this. So we play a sound and I'll play the sound for you in a moment, but I'll describe it first, and I don't want to shock anyone with the sound, which just sounds like white noise, like a shh sound. Then we play another sound, which is the white noise, but it might have a tone in it, like a pure sinusoidal wave, just like sounds like maybe a flute. And then we play another sound with white noise. So then we ask which sound had the tone in it. And if you get the question wrong, the tone gets louder. If you get the question right, the tone gets quieter. And what this does is it helps us to kind of identify a threshold for auditory sensitivity in a given person at a given time. So and we do this all over your phone or your laptop if you want to. And this is a pretty decent measure of the sensitivity of the auditory system. And also aligns with a lot of the complaints and concerns people have had with auditory experiences. Too low and you're insensitive, too high, there's too much activity, you can't distinguish signal from noise. And now I'm going to play what this sounds like. So just so everybody knows, and you can participate if you want, tell me which sound the tone is in. So that's what it sounds like. And just hear this over and over again and say, which sound is it? And here's what the data look like. Oh, I see sorry, I'm seeing in the Q&A, how do you control for volume and decibels in the auditory task? That is such a great question. I'm so glad someone asked. And I'm happy to talk more about it. But one of the reasons we came to this task is that to some extent we can't control. So we have people set a comfortable noise level at the start of the experiment, because people are going to have different headphones, different phones, they're going to have volume set differently. And so if we were just going to try to get measures of absolute auditory sensitivity, it would be impossible without sending identical hardware to each person and making sure it was all set up and executed properly. Here, what we're doing is we're trying to get this relative sensitivity of distinguishing or really sort of filtering the sound sensitivity, which is, I'll show you what the data look like from 2 pilot participants, just so you can see, I'll show you more in a moment. On the left, this is just 2 different people on day 1 and day 2. The y-axis is the tone volume relative to the sound. The x-axis is the number of trials they've heard through. And you can see that everybody sort of, gets closer and closer and closer. They get better and better till they get to a point where they start getting them wrong, right? This is sort of, they converge to a threshold point. Lower is more sensitive. It's not necessarily better. And again, as I point out, the noise is always the same volume because, well, the noise in a given person during the experiment is always the same volume because everyone will have different headphones. Their phones might be at different volumes. So the absolute intensity is inevitably going to vary to some extent among people. All right, so some preliminary results. Currently, we have 50 participants, 14 autistic adults, 36 neurotypical adults between the ages of 18 and 45. We have them do this every day for 2 weeks. We ask them about the sound sensitivities. We give them the simple tasks. And we also, when they first start the study, we include some traditional sensory measures. We also do, to the technical question, we do what's called a headphone check before the experiment, which is a little way of determining whether or not someone's wearing headphones when they're doing the experiment. If you were just doing this without headphones, the ambient noise in your environment might be so great that it would be impossible to make sense of that data. All right, so the good news is that this works. So each one of these little squares is a person doing the experiment, and almost all of them show that expected hockey stick shape. What we do with these data, well, the first thing we find places, I don't know if you can see my map, where the line back, meaning it goes up or it doesn't. Why that happens almost 10 hit using headphones, and so we exclude the data. It's again very high rate of success across people. We take average intensity or the average value of their sensitivity in the final 10 trials and use that as an again, this is a sort of interesting psychophysics task, but up until now, you had to do this in the lab. And so now people can at home, or hopefully at home, we hope not. So some results. So first, improved average performance, right? If we just within individuals, by group, but these measure sensitive in all these plots. It just can get a little confusing still for me sometimes. But if we look at symptom changes, meaning things like I had to leave work today because of sound, and these are again measures like 0, 1, 2, 0, 1, 2, or 3. So we're using normalized entropy as a measure of variability, and we're seeing significantly increased variability in symptoms in autism. And we're also, so if we kind of go down into our symptom domains, our specific questions, we're seeing some interesting things, seeing increased in autism on the left, increased variability in anger, increased variability in understanding speech and noise. We're not actually seeing group differences in noises being too loud, but we are seeing larger differences in people reporting sounds being too quiet. Now, this is the variability. The point here is that this means not that people are experiencing angry responses more, it's that they're more variable in experiencing these angry responses. Sometimes it's fine, sometimes it's not. Whereas in the neurotypical group, we're seeing much more stability within individuals. Just briefly, these standard measures correlate, standardized measures, and this is the adult sensory profile, for example, correlates highly but imperfectly with daily concerns. Each facet here represents a day. The y-axis is the daily concerns. The x-axis is the adult sensory profile. It's a good correlation, but it's not perfect. So there's some variability in our day-to-day experience that's not being captured. And then finally, this is a little bit of an unusual plot, so I'm going to just take a minute. So this is showing an aggregate of all of our points over 2 weeks for daily concerns. We're using a regression model that's accounting for the fact that we're measuring from the same people over multiple days. And on the y-axis, we're measuring our daily auditory concerns. So this is on average. We're just taking, for a given day, broadly, how much people endorsed I had left work, sounds bothered me, I had trouble concentrating. And then on the x-axis, their auditory sensitivity is measured by this task. And we're finding that days when you're more sensitive, in our objective measure, are days when people are reporting more concerns. And this is, I think, that I'm really excited about this. Like your auditory performance, this objective measure of like how you're experiencing sound is tied to this subjective report, right? I think it's really starting to bridge a gap in the between these two things that we've been trying to bridge for years. Like people have complicated experiences that they describe, and now we're able to objectively measure it across people. You're more sensitive on the days that you're not feeling your best is broadly what this is showing. So where do we go next? Well, we're still trying to now understand the neural mechanisms about this, right? And we've talked about how these things fluctuate from day to day to day, but they're also fluctuating from moment to moment to moment. And that's the next part of it. So these are very, very preliminary data on how we can get a little closer to these mechanisms, early findings, but promising directions. So remember the auditory cortex really, really quickly. 100 milliseconds after you hear a sound, there's this thing we can measure in the EEG, this N100 response. It's a negative bump around 100 milliseconds after you hear a sound. It's larger when a sound is louder to you. It's a very fast response. It's very reliable, and it's generated by the auditory cortex, right? It's sensitive to the state of arousal, right? To how someone is feeling, like awake, sleepy. It's well studied in autism, and in many conditions. Consistent differences haven't been identified. But if you recall, we also have other mechanisms that, sorry, a little too quick there, that regulate our sensitivity in the auditory cortex. And so briefly, I'm going to point out here, we have the locus coeruleus system. This is this brainstem region, generates norepinephrine, and it changes the excitability of neural assemblies throughout the brain. In general, it increases sympathetic arousal, things like heart rate, sweating, wakefulness. It's associated with stress responses, associated with emotional responses and anxiety and attention. And in general, when we have more excitability in the auditory cortex, we get bigger N100s. Again, this is mostly from animal research here. There's less research in humans. The other important thing is that this activity, these systems just fluctuate from moment to moment throughout the day, even outside of these extreme states like sleep. Now the LC is deep in the brain, so we can't measure it with EEG. We can measure it with pupil diameter, which can serve as a decent proxy for locus coeruleus activity. We can measure it in a few ways. We can flash a light to see how much the pupil changes, or we can keep the light the same and just see how little fluctuations in the pupil change. So briefly, pupil diameter, differences in it are associated with autism. And on the right, this is just a plot showing differences in the latency of the pupil response to light in a paper we've done with 400 children, indicating there's altered dynamics of the locus coeruleus system. So again, within the auditory cortex, the locus coeruleus, there's inconsistent evidence for differences in these systems within autism for increased or decreased activation, limited consistency in the research. And so we think that the measurement of these systems in isolation might be insufficient. We thought, okay, but if the locus coeruleus, right, if these arousal systems are changing our auditory sensitivity, maybe fluctuations in arousal change sensory sensitivity differentially in people with auditory sensitivities. So we did this with a really, really simple task. Takes about 20 minutes. Is we measure your pupil diameter. So this is now, we come into the lab for this. This is EEG and eye tracking research. And then we measure your EEG, and then we just play some beeps. This is modeled off basic research, basic animal research. And the data I'm going to show you is very preliminary. It's from 9 neurotypical adults. This data has been processed. We have more in the queue. And again, still actively recruiting for this. We're co-registering pupil diameter and EEG, and people just look at a screen and listen to beeps. So first thing, just validating our approach. When you have a bigger pupil across individuals, you actually have a bigger, greater magnitude response to sound, right? So this is validating this approach, and we're capturing a mechanism in each person for how arousal modulates sensory sensitivity. But here's the thing that is more interesting. We estimated something that we're calling sensory modulation here. And this is the amount that your N100 changes when your pupil changes. So this plot has been stretched out to sort of highlight that we're measuring this difference within a person. based on how much their state of arousal is changing. And we find out that in people who have increased sensory modulation, they also, which again, the axis here is a little tough to follow because the N100 is negative. So that means more negative, show greater sensory sensitivity, right? So this is really indicating that the more arousal increases your sensory response, the more sensory sensitivities you report. This also associates with our day-to-day measures. The effect of arousal on sensitivity is associated with sleep quality, and it's also associated with how people are experiencing distracting sounds from day to day. I'm trying to speed up here so we have time to see a lot of Q&A questions. So, but preliminary results, we're finding that the magnitude of this modulation, and now we're like from moment to moment to moment, not from day to day to day, predicts increased report of sensory sensitivities. And they're associated with how much variability experienced from day to day to day, right? So we're seeing these symptoms, they do tend to fluctuate more in autism, and it tracks with these objective measures. And these really, really rapid changes in arousal and sensory sensitivity also associate with symptoms. And so a few things. One, it looks like, measuring this multimodal measurement is really important for capturing these dynamics of how the system unfolds. But let me tell you how the way I kind of think about how this must feel, this phenomenology of this, right? This suggests to me that maybe for some people, their sensory experience is more volatile, right? If you're more hypersensitive, if you're always hypersensitive, then you can just always wear earplugs. I'm not saying that's okay and like acceptable and the only approach, but it is it is an approach. Or again, if you're hyposensitive, we have hearing aids. But so what if you're experiencing these more extreme states? Then it's hard to know what to expect and challenging in how you're going to prepare for that. And so my hope with like kind of understanding these mechanisms is we can start to work towards information that's useful for people to kind of plan out how they're going to approach and conduct their day-to-day lives with these sensory sensitivities. For example, you could think maybe if we were to track these regularly, we could come up with something like a sensory weather report, right? Where we could use wearable devices to track stress and maybe predict when people might be more vulnerable and give them a heads up, or just develop more sensitive measures so we can assess the efficacy of interventions or treatments. So next steps, I've given you this has been a constricted age range, but we know that these symptoms change in childhood and later in life, and we're starting studies incorporate a wider age range. Secondly, there's some specific ways that we think arousal is differentially changed in misophonia. We're starting up a new study in the fall for that. Third, we've done a lot of work myself with Jamie Partland that I haven't barely mentioned in developing biomarkers for use in clinical trials. In the past, we've been primarily concerned with social aspects in autism, but we have a team interested in using this approach in the context of developing protocols for clinical trials. We're looking towards developing finer temporal sampling, not just at the end of the day, but throughout the day. One thing that is very interesting is that many people who come in for these studies are on a range of medications that they're using to address multiple symptoms, and so we're looking to really try to take that information and see if we can identify how those medications may or may not be impacting these biomarkers. And now I'm just the hood ornament on a tremendous amount of work. This is not everyone, but most of this work reflects so much effort and help from everyone here, and particularly participants in our families, our supporters have been wonderful. And then thank you. This is a QR code. If anyone's interested in participating, they can scan or email Bella. And I'll be here for more than 3 more minutes to answer questions. So now I will go to the Q&A, and now I'm going to start. And Denise, let me know if I'm allowed to stay for at least 10 more minutes because there's quite a few here.
Yes, you can stay
Okay. Okay. All right, I'm going from the top. I think I answered what I meant by auditory sensitivities to David, but let me know if I haven't. Uh, I I can speak that I'm not sure what the effective treatments there are for misophonia. That's a question that the chat is, can you speak on misophonia and effective treatments? I've talked to people who many other people have asked me this question, and I'll stop the share, I guess. That makes it easier. A few other people have asked me this question, and I've spoken to them. I'm not sure what effective treatments there are. The people I've spoken to haven't identified anything that's been effective generally for all of their issues. So anonymous attendee, my son wears noise canceling headphones almost all the time. We've noticed that he's sensitive to some sounds only. Some loud noises don't bother him at all. Is this common? So this is a theme that seems to come up in the research that I described. And I have and Denise, I can give you a list of references for everything in here too, which might be helpful for people. I actually have it in another document right next to me, but it was so long, I thought it would just be overwhelming. This seems to be a consistent theme in that it's not, these sensitivities are not well described by simple hyper or hyposensitivity, and they seem to wax and wane from time to time. What are some new evidence-based activities we could use with children and adults in ASD? I do not do treatment, and so I don't want to speak to what those would be. I can try to find maybe some reasons I can ask around here, but I don't know what. I haven't found anything that seems to be a consensus in the literature as a strong evidence-based treatment for these kinds of sensitivities. Maybe that's the best way to put it. David J. Levitin in his book, This Is Your Brain on Music. I think I have that book from the 90s. He states that auditory sensitivity may be the highest sensory sensitivity because of the way sound is processed directly. The frequency is brought to the ear, whereas the senses like visual color is not by the brain through the eye. I am familiar with the book. I remember loving it. I can't remember a lot more than that because it was almost 30 years ago now. Someone asked, is a scale available? And I think they're probably asking about the hyperacusis questionnaire, which is, there's actually, I think, more than one measure with the identical name. But you can, it is freely available. If you would go on Google Scholar, I can put that reference in and give it to Denise as well. Someone asked, why is a child sometimes bothered by people chatting and sometimes tolerate it? Well, I think this is kind of what we're trying to get at, is the system that seems to modulate why this happens. And so thus far, it looks like there's, in autism, more variability in these sensitivities, and they appear to be associated with these arousal-based systems. So I think there's two comments here that are responding to another comment I said. Okay, great. Gustavo is asking, how can sensitivity be measured if the person is nonverbal? This is a great question. We're trying to, so one of the benefits of these lab-based measures, pupillometry and EEG, is that they don't require overt verbal responses. And so we're actively trying to make these experiments more accommodating and accessible for nonverbal and minimally verbal people. So that's one approach. We are also trying to develop ways we can do this, with our smartphone-based measures, but we're still sort of working on finishing up data collection with this adult cohort, as I mentioned. There's a question about pandas, flares, and pathogens. I apologize, that's not my area of expertise, and so I'm not sure. I don't know the answer. The age range for the big NIMH study. What is the age range for the big NIMH study? So that data was, it included toddlers through adults. I apologize, I don't offhand have the highest. I don't have the upper age range captured in that data set, which is a great question. So how to differentiate between sensory sensitivity versus processing delay. So I think so. I'm not sure exactly. I guess this is maybe again one of the goals I'm trying to achieve here is really more specificity in the taxonomy about what these terms mean: sensory sensitivity versus processing delay. And so there's a challenge in sort of the way these terms are used in different contexts in research and education and in clinical work. So are these correlated? So I hope that answered the question. Again, like if not, please let me know. So are these correlations of low to high also correlated with vagal nerve effects and efficiency and regulation? I don't know. My guess is, given the way that many of these arousal related systems are intertwined with vagal nerve, that there's probably some association there. However, we're not directly measuring that. So you can measure what you see, but not what you can't see. So behavior observation is not the whole story. That is I'm not, I guess broadly, a lot of the neuroscience tools we use are trying to measure things that are more difficult to observe from direct behavior. Also, behavior can be multi-determined. The same behaviors can emerge from multiple underlying etiologies, and so that's one of the reasons why we use these tools. So I think I hope I answered the term. Someone said they didn't understand the statement regarding triangulation. I think that the terminology was maybe just a little not great at first, but I hope that's been covered. So there's another question about anxiety and autism with hyposensitivity, delaying the time in their processing with reaction. Again, I think that that it's an empirical question, and how we would define delay and sensitivity and reactions would be, that's where I would want to start, like really formally operationalizing those terms. I do not have thoughts or comments on visual snow syndrome. I apologize. Someone is asking if this is done as an assessment, I think. So this is part of a research protocol. We hope that these approaches we're developing can be developed and have more translational uses, be formalized so that they're easier to apply outside of being in a neuroscience lab. But right now, it's not a formal assessment. I think I answered the question about controlling for auditory tasks. One person is saying that their child suffered increased sensitivity to electronics after doing biofeedback therapy. I'm not sure. This would not be my area of expertise, but I'm not aware of any connections with any specific kind of equipment. So this person is saying they're a high masking autistic woman who struggles with sound sensitivity in their everyday life. They wear earplugs to walk outside for noise. They recently had a adverse reaction in an MRI machine. They couldn't complete the test because of the sound sensitivity. So just to give everybody context, MRI machines are loud. So it's, you get your head in there and it's this loud clanking in mechanical noise. It's a little bit unusual. It's pretty loud though, and your head's right in the middle of it. I did have hearing protection, but it was inadequate. I wonder if I think, yeah. So, they wonder if anyone else has thought about the specific issue with MRI machines. I know that people have adopted different approaches to attenuating the sounds of the MRIs with noise sensitivity. I don't have, I mean, this would be, these would be specific to the particular MR center, but there's a range of ways to attenuate sound response. And I would just ask next time if you can wear earplugs in, which may work better than often like kind of the over ear earmuffs that are offered. Are there treatments or therapies that have proven to be effective with auditory processing? So I am not aware of a consistent and agreed upon set of treatments or therapies that are effective with auditory processing. But again, I don't want to say that there aren't any because it's not my area of expertise. So there's a specific question. Someone's son is complaining when they take a deep breath while walking upstairs. Complains their voice is too loud when it's a normal tone. He's okay if I tell him ahead of time when I need to vacuum. He put felt stickers on our door frames to make them quieter. So this person's describing a range of auditory concerns. The question is for any treatments that I can advise. I apologize again. I can't advocate. I don't know of specific treatment that would be effective for an individual. One person is asking me to address the long-term harm of noise canceling headphones. I am not aware of any research. That's not my area of research. So on the long-term harm of noise canceling headphones. We do, yeah. So someone is saying, thank you. They're saying this is, they really like to talk and asking if we collect behavioral measures of autistic traits. We do broadly. We collect self-report and in the lab, clinician-administered measures of traits that are aligned with the DSM-5 diagnostic criteria for autism. So there's a question whether eye flickering indicates general sensitivity. I'm not sure that. And there's a question, does gentle scaffolded exposure therapy work in reducing sensitivity? I don't, this treatment is not my area of expertise. I would always ask a clinician who knows you or your child well. So thanks everyone for coming so much. And if there's any other questions, then happy to answer them. If not, then thank you so much for having me.
I think that's all the questions today. Thank you so much for doing this presentation. It was great to have you, and we look forward to learning more about the work that you do in the future and having you back for another webinar.
Thanks. All right. Bye,
All right.
everyone.
Take care.